Okay, let's dive right in. 5,000. That's the staggering number we're kicking off this explainer with today. 5,000 is the amount of shaft horsepower produced by just one of this incredible aircraft's modern engines. I mean, it's a massive amount of energy. And as you can imagine, controlling it requires an absolute symphony of mechanical engineering.
And nothing illustrates the harnessing of that wild power quite like the CH-47 Chinook. You know it when you see it. This iconic beast of a military helicopter was introduced all the way back in 1961, and since then it's accumulated well over 1.5 million flight hours. It is purpose-built for heavy lift missions, capable of literally pulling an astonishing 10 tons of cargo right up into the sky.
So today, we are going to trace the incredible energy journey straight through the Chinook's highly complex powertrain. We're going to map exactly how that furious power travels from the jet turbines all the way out to the tips of those 60-foot rotor blades, entirely without tearing the aircraft apart.
Section 1. Breathing fire. The T55 engines. We actually have to start our journey at the very back of the aircraft, with the lungs and muscles of the Chinook, those twin Lycoming and Honeywell T55 turboshaft engines. To generate that massive 5,000 shaft horsepower, these engines follow a highly efficient four-step cycle. First, they pull in absolutely huge amounts of atmospheric air. Then, they compress it down to a significantly smaller volume and way higher pressure. Third, they mix that highly pressurized air with fuel and ignite it. And finally, they use that high-energy explosive gas to spin a turbine. If you look closely at the internal architecture doing the work here, you can actually trace the axial compressor, where the air gets squeezed, right back to the turbine rotors. This is the exact spot, the crucible really, where explosive thermal energy is converted directly into sheer rotational force. Now, to get this power out of the engines, the energy first travels via a quill shaft into the engine transmissions. The whole goal right now is just to route this power away from those engines and push it toward the center of the aircraft. But before that energy moves any further down the line, we have to stop and ask a pretty critical question. Imagine you've got 10 tons of heavy cargo hanging beneath you, or, 44 combat-equipped troops sitting in the back. What happens if one of those two engines completely fails mid-flight? Well, the solution is brilliant. It's an ingenious little device called the sprag clutch, and it's located right inside the engine transmission output shaft. It's basically a one-way drive mechanism. So if an engine dies, the sprag clutch instantly and automatically disengages it. This guarantees that the dead engine's weight and drag doesn't just pull the spinning rotors out of the sky. It allows the pilot to safely perform an autorotation or just keep flying on the remaining engine. So, once we're safely through that protective clutch, the energy meets its first major directional shift. Spiral bevel gears inside the engine transmission take that rotational energy and sharply turn it 90 degrees. This sends the torque pointing directly inward toward the center of the helicopter, traveling right through the engine drive shafts.
Section 2. The combining transmission heart.
This brings our energy journey to the absolute core of the helicopter, the combining transmission. It sits right in the dead center of the powertrain, bolted securely to the fuselage. And really, this is where the magic of the dual rotor system begins to take shape. It acts as the critical junction point where the torque from the left engine and the right engine finally meet up and become one single unstoppable force. Inside this heavy-duty, oil-cooled gearbox, you'll find two spiral bevel input pinion gears. They receive that brutal torque from the left and right engines. But here's the cool part. They don't fight each other. Instead, they merge their power by simultaneously driving a single, unified spiral bevel ring gear. Now, the crucial takeaway here is that the combining transmission doesn't just merge power. It conditions it. By driving that larger ring gear, it applies a 1.70 to 1 speed reduction. This is the very first step in taming those furious engine RPMs down into something a helicopter rotor can actually use. Section 3. Synchronizing the spin. Okay, so now that we've created this massive, unified flow of energy, we need to distribute it, and we have to do it with absolutely flawless precision, using what we can basically think of as the Chinook's nervous system, the synchronizing shafts. These are long, seamless aluminum alloy tubes running directly along the top of the aircraft. They grab that combined power from the center and send it out to the absolute front and absolute rear of the helicopter. To span this massive 52-foot aircraft, the forward shaft uses 7 distinct sections, and the aft shaft uses 2. These highly balanced, lightweight sections are joined together by flexible stainless steel couplings. And this design is so smart because it actually absorbs the natural flexing of the aircraft in flight while making completely sure the power reaches both ends of the helicopter at the exact same time. It guarantees the two rotor systems stay in perfect, unbreakable rhythm.
Section 4. Rotor heads and left.
Following those shafts, the energy has finally reached the extremities of the aircraft, the forward and aft main rotor transmissions. This is it. This is where the actual heavy lifting is going to happen, translating that raw shaft horsepower into the aerodynamic lift that makes flight possible. Inside these two massive gearboxes, the energy makes one final critical change. Using another set of spiral bevel and planetary gears, the torque is cranked from a horizontal plane up into a vertical spin. And during this turn, the transmissions utilize 3 distinct stages of speed reduction, massively, and I mean massively, increasing the lifting torque available to the rotor blades.
Now, a traditional helicopter needs a hale rotor, right? Otherwise, the body just spins wildly in circles. But the Chinook doesn't have one. Instead, the forward rotor spins clockwise with a 9-degree forward tilt, while the aft rotor spins counterclockwise with a 4-degree tilt. By spinning in opposite directions, the rotational torques perfectly cancel each other out. It keeps the whole aircraft completely stable.
But hang on a second. If you look at a Chinook, the spinning diameter of those blades is 60 feet, but the helicopter itself is only 52 feet long. So how do these massive overlapping blades not just literally destroy each other? Well, the secret is vertical spacing. The aft transmission is mounted on a pedestal exactly 19 inches higher than the front transmission. Combined with that perfect synchronization we talked about earlier, this 19-inch rule absolutely guarantees they never intermesh or collide.
The final step in our journey pushes the energy straight up through the aft vertical drive shaft. It's externally splined at both ends, connecting the transmission below right up into the rotary wing hub above, delivering that incredible torque out to the 3 massive fiberglass blades on each head. And that brings us to our final magic number, 225. By the time that blistering 5,000 horsepower from the jet turbines reaches the ends of the 60-foot blades, the complex gearing we just traced has perfectly reduced the speed to a steady, incredibly powerful 225 revolutions per minute. At this precise speed, the blades produce the lift required to hoist 33,000 to 40,000 pounds of gross weight into the sky.
As we wrap up this explainer, it's pretty wild to think that this intricate energy journey was first engineered back in the late 1950s and early 1960s. And the craziest part? Today, Honeywell actually has upgrades in the works to push these engines to a staggering 6,000 shaft horsepower, essentially doubling the operating range for max payload missions. It really just leaves us with a fascinating question. Just how much more powerful can the legendary Chinook become in the decades ahead? Thanks for exploring this engineering marvel with me.